So the exam sheet is right there. The solution sheet, you can take it. If you have questions later on, you can talk to the TA afterward. This is your. Oh, this is the exam.
Yes.
No，我是手写。
那个 Patel 把它改成这个。
OK OK。我们想说那个直接哪里？Okay, so I gave the TA a written exam sheet. They changed to typed exam sheet. Okay, which is good. So there's a material with yielding strength. This symbol, Poisson's ratio. This symbol, the material under tensile test with the load of F. And the stress area is A, determining safety factor, which is larger than or smaller than what number, which design model did you use. If you change a different model with the answer change, show why. And the solution. So here's my solution. Just one. There are multiple ways to solve this. I'm not sure if the TA follow what I mean. So basically, you can choose. We have learned three different models, right? You can choose any two or any three. That's fine. Supposedly, they should have the same answer. Okay, and let me show you why. Now, this is first you should follow the maximum shear stress model. This is just to test you whether you know under the condition of tensile test, actually the safety factor is always the same. It's not directly mentioned in the class, but if you realize it, because this is a plane stress problem and only stress along one direction, so definitely the principal stress is sigma. Okay, so there's the second principal stress is 0. So the Mohr circle always looks like this. And as I mentioned so many times, we have used this concept multiple times. The Mohr circle for tensile test is an important concept in the failure model. So the Mohr circle, this is stress, this is shear stress. For tensile test, Mohr circle always looks like this. And here is your principal stress 1. And this is gonna equals to the stress that has been applied to the material. And your S2 is always 0. Okay? No matter what model you use, at the end, you end up with the same equation. So this is by maximum shear stress model. In Mohr circle, the maximum shear basically is 1/2 of the sigma, okay? And this has to be smaller than the yield strength divided by 2 over safety factor. Okay, so that's why it's like this right there. So you have to answer n is smaller than this value. Okay. In the problem I mentioned, is this smaller than or larger than? just to test you whether you know it has to be smaller than. Okay, and this is based on maximum shear stress model. And if you use maximum strength energy model, which is where the equation looks like this, at the end you have S1 smaller than sigma y over n. That's the exact same equation. And let's say if you use maximum distortion energy model, at the end, S1 squared plus S2 squared minus S1, S2. This is also S1 and smaller than yield strength over N. So, in many exams, when the problem asks you to compare, usually the answer is, oh, not the same. And the problem will ask you to explain why. But this is a special case. I give you a problem where you actually have same solution. So you can say, okay, same. And in the problem I said, explain why. You can say that because there's only first principle stress, second principle stress is 0. So in all three models, it ends up with the same equation. That's why the safety factor is the same. Okay, so that's a simple first problem. Now, let's take a look at the second problem. So there's a shaft that is carrying a load F located at one third of the entire length, and then the load is F. Determining reaction forces F R1 and R2. Determine maximum bending moment. Where is the location of the largest tensile stress along X direction? So somewhere that is being pulled from left to right. Where is it? The shaft is also being twisted by a torque of T, as shown below, and then study the first and second principal stresses at that position with the maximum tension stress. The yielding strength is sigma y, and so if we want the safety factor to be equal 1.5, so what would be the I don't know why you changed my wording. Okay, the shift must be larger than what? So over here, do you understand what the problem is about? Basically determining the diameter. The shift must be thicker than one level. Okay, so the safety factor equals to 1.5. And here I especially mention use maximum distortion energy model. And there are some equations given right here, but not indicating which one is which. So let's get back to the solution. So from the drawing, it's very easy to determine reaction forces. Basically, the left side is 2/3 of F. The right hand side is 1/3 of F. Okay? And then if you draw the shear stress a shearing force diagram. It's gonna look like this. And if you draw the bending moment diagram, it looks like this. And you can very easily get the linear equation of the first portion, where the slope is gonna be 2/3 of f multiplying the distance. And then you can plug in the position L, where you obviously see there is a peak of the bending moment. So you plug in L, then you get the largest moment equals to 2/3 of F times L. So that's the largest value. And right at, you need to mention, okay, on the shaft. So the shaft looks like this. Right. And here's the force. Here are the reaction forces, R1, R2. So it's the shaft is being bended in this way. Right? So you can obviously realize here is compression and here is tension. So if you want to make a drawing, here is exactly the position. That's where the material is being pulled left and right. Okay? So, when you have a drawing like this, actually you are eyeballing from the bottom. This is the eyeball. Okay? You are viewing this from the bottom. And what you see is gonna be the material is being pulled left and right, and here is your normal stress due to the bending moment. So this equals to 32 m pi d cubed. Okay, I use capitalized D for this problem. And then, as I mentioned, there is a torque right here, right, being twisted. So there will be torsion. There will be shear force like this due to the torque. And the shearing force equals to 16 T over pi d cubed. Yeah, as what I have written on the board. And you already know the amount of M from the problem solving. So you just need to plug in here. M equals to 2/3 of FL, just plug it in. So you end up with these two values. Then you can draw a Mohr circle. Okay, and this is how the Mohr circle is gonna look like. You can first find the position of the center point, which is half of your sigma. And then you can use a triangle to determine the radius. So over here, you can just write down the whole equation. Right? This is the radius. So the principal stress one and the second principal stress can be determined by the center point plus the radius and center point minus the radius. So these are the expressions of first principal stress and second principal stress. And then the order is wrong. Okay, and then over here. Now I ask you to use maximum distortion energy model, which is this one. So from here, the problem was what? determine the shadow. Oh yeah, determine. So what? The yield strength must be larger than what? So the safety factor, when the safety factor equals to 1.5, the yield strength. So it's like it's about, the problem was about selecting the material. So right here, from the maximum distortion energy, you can determine, so sigma y must be larger than whatever equation you have inside the square root. Now moves to the right hand side, and your safety factor is 1.5. Okay, so this is basically the answer, but you need to plug in what you got earlier. And those are, of course, they are in symbols, not numbers. So actually, in your exam, you don't really need your calculator, just plug in equations. So you need to be patient and just derive your equations. So that's the answer. Is it everyone okay? Yeah. So I thought you will get 10 points. It's not very difficult. Okay. Anyway, if you have questions about the grading, you can ask TA later on. Now we are moving on to the today's lecture. So yesterday we learned about 3 different models of fatigue model when the material is under dynamic loads. So we are back to the problem that we used for many times in the past. Let me remind you what the problem was about. There are 2 bearings on the side of the shaft, and there are 2 pulleys. And the pulley is being, there are some belts on the pulley, and the tension force on both sides of the pulley is different. Usually it's different. Because there is a difference of the force, so there are some torque. So it rotates it's supposed to rotate the shaft. However, the problem mentioned, the shaft is not rotating. Okay, so it's like there is a tension force imbalance. So it's like the shaft is being twisted, but the motor is not running. Okay, but it's a very weird situation. The tension force changes. So it's like you're trying to twist the shaft, and the twisting force is dynamically changing, and it's like you twist the shaft so in a certain way so that the shaft is not rotating. Usually it doesn't happen, but it's just a math problem. Okay. So if this is the situation, over here it's telling you the belt tension loads fluctuate between the following two conditions. So it's like, okay, there's a moment 1 and moment 2. So at a certain point of time, the amount of the twisting forces, the belt tensions, are in condition 1. And then in some other time, it changed to condition 2 and goes back and forth. So this is a way of the how the problem describe the fluctuation of the load. Okay, if you want to make it like a drawing, it's like this. This is time, and this is W1. So sometimes it's 5, sometimes it's 8. So it's like how the W1 fluctuates, but it doesn't. For us, we don't really need to know the function. We just need to know the range. Because for us, we only care about the extreme case. Okay? From here, we can tell what's the average and what's the amplitude. Okay? So this is how you solve it. We are out of time. Give me 2 minutes. So this is exactly what we have solved the problem. Okay? But you have to, it's like you have to solve it twice. You solve the problem with condition 1 and condition 2, and you realize the shear force varies in this range, and the bending moment varies in this range. Okay? So it's like solving two problems. Like solving the problem with two sets of parameters. Okay? And over here, if you observe the Mohr circle, it's like the Mohr circle change its shape. Changing the shape. Okay? So you can kind of realize the mean value of the first principle stress and the mean value of the second principle stress. Okay? And also the amplitude. But this is a kind of an estimation. So we kind of separate the mean value part and the amplitude part. And you plug in all the equations that we used earlier. So with that, I didn't tell you yesterday, when we have the design equations, we mentioned we have the average part over some limit, let's say y plus the range part over endurance limit, right? So over here, please pay attention to these. We only have normal stress right here, no shear stress. But if you look at the original problem, there's actually shear stress. So how do we use the fatigue model if the model doesn't have the term for shear stress? So what we are doing in this part of the lecture is, for all the model values, when we need normal stress value here, we use von Mises stress. And what is von Mises stress? Basically, for plane stress problems, it's this value. This is for plane stress problems. So we use the equivalent stress that covers stresses in all directions. So I think this is the key for this part of the lecture. Okay? So I know it's at the end of the, well, I'm out of time. So please go back and take a look at this part. Okay? The reason why we determine von Mises stress is because for tick model, there is no shear stress term. So you need to use von Mises stress equation to cover stresses occurred everywhere. Okay, so I hope everyone is listening because this is basically everything about your exam 3. If you know how to do this, then you're fine. Because later on, I'm just going to give you some problem. You just need to know, okay, I need to solve for von Mises stress, and then plug it to the right equation. If you know, then you're fine. Next lecture, I'm going to talk about stress concentration factor. We are going to make these equations a little bit more complicated because stress concentration matters in fatigue. So that's for next week. Okay, so this week, please take a look at this slide and make sure you know how to solve it. It's not very difficult, but sometimes if you don't know, you just don't know what to do. Okay, that's it. Okay, thank you.